We're going to look at another example using the precise definition of a limit to prove that a limit exists and what it is. And so our example says, let's look at the limit as x is approaching -3 of 7x minus 9. And this is equal to -30. Okay, so we're trying to find some delta. Such that, so ST is a way I use that as such that. There's actually another terminology that you will kind of see, I believe is kind of like this, but let's in math, but let's not do that. So find delta such that delta is greater than 0 and x minus a, the absolute value of that is less than delta, where f of x minus L is less than epsilon. Okay. So again, it's helpful to go through and kind of pick out what you have. So this is our f of x function. So we have this 7x minus 9 in here. Minus L, so minus, well, our L value in this case, that was this -30. So minus a -30. We want to end that absolute value. And we want this less than epsilon. So our goal, then this is just the scratch work. Our goal is to get this to look like absolute value of x minus a. And in our case, that x minus a, our a value is this -3. So in our case, which is equal to x minus the -3, or x plus 3. Okay, so we're going to manipulate this absolute value to look like x plus 3. Once we're able to manipulate it to get it to look like that, whatever is on this right-hand side of the inequality is what we're going to choose delta to be. So I would just go through first by simplifying inside my absolute value. So I have 7x minus 9. Well, minus a negative is really plus, so plus 30. And that absolute value is less than epsilon. Combine like terms, so we have 7x. Well, -9 plus 30, that's positive 21, is less than epsilon. So we're almost there. Notice that both of those terms inside have a factor of 7. So we can pull that 7 out. So we would get parentheses x plus 3. So absolute value 7 times the quantity x plus 3, and that absolute value is less than epsilon. So again, 7, that's a positive number. Absolute value of 7 is just 7. And so we can say, well, this is just the same thing as 7 times the absolute value of x plus 3, which is less than epsilon. And so divide both sides by 7, we get x plus 3, that absolute value is less than epsilon divided by 7. Okay, so now we figured out what we need to choose delta to be so that this is always a true statement. So we want to choose delta to equal epsilon divided by 7. And we can start our proof. So if we choose delta to be equal to epsilon over 7, and we know the absolute value of x plus 3 is less than delta, so then x plus 3 would have to be less than epsilon over 7. And our whole goal is to get back to what we had originally started with. So multiply both sides by 7, we get 7 times the absolute value of x plus 3 is less than epsilon. This is a positive number. We can put it inside the absolute value. So 7 times that quantity, x plus 3, is less than epsilon. Distribute. So 7x plus 21 is less than epsilon. We're trying to manipulate this to look like f of x minus L. And so again, we're trying to manipulate it to look like this. And so we can do that by rewriting 21 using -9 plus 30. So 7x plus, and so instead of writing 21, I'm going to write it as -9, okay, or plus 30 minus 9, just for now. And I'll rewrite the order in a second. And that absolute value is less than epsilon. So the absolute value of 7x minus 9, which is our f of x function, instead of writing plus 30, we're going to just write it as minus a negative 30, is less than epsilon. And we just showed that for that delta, f of x minus L would be less than epsilon. So we're done with the proof. We can put that little square there. Let me see if I can pull up and us kind of looking at this graphically. Let me pause the video for a sec. Okay, so I just kind of want us to look at this and what's going on. So our function was 7x minus 9. We have a line. Let's look at this. So 1, 2, 3. So I know here, just because this is in the form of y equals mx plus b, I know my y-intercept is -9. I know my slope is 7, or 7 over 1. So if I rise 7, I would go over 1. Okay, and I want to look at -3. I know when I plug in -3 in there, I get -30. That's where I didn't want to. So that would be 10, 11, 12, 13. That's why I really didn't want to do this. 4 to 5 to 6 to 7 to 8 to 9, 30. Okay, down here, not down there, but that's where -30 is. Over here. Okay, so we have this line. If I can make it straight, I'm trying to make it straight. I know you guys have great imaginations and you can imagine that straight, right? Oh my goodness. And it said, we want to figure out how to always be in this interval. This is our L value. We needed to choose what delta is so that we're always in that interval of epsilon. So what if we had chosen let epsilon equal 1? So basically, if epsilon was equal to 1, usually we want it smaller, but I just want to show you. So if this was equal to 1, then we want to be in the bounds. We want to choose delta so that we're in this bound that we're always going to fall between -29 and -31. So if I look at this and I come up here, yeah, this is not a great picture. You just got to kind of deal with me. Gosh. And we come over here, we hit the graph, we would have something within here. Basically, this epsilon or this delta that we need, we have to stay within this interval. And this interval was epsilon divided by, we had epsilon divided by 7. So delta was equal to this. And so in our case here, we would know that delta, if we were choosing epsilon to be 1, would equal 1/7. And so I would have to stay within this interval, I would go to the left 1/7 and to the right 1/7 from -3. And so I could figure out what these values are. And anything you chose, getting closer and closer, you would always be within that bound if epsilon was 1. But we're trying to actually usually get epsilon infinitesimally, let's say that, small. Okay, so there's sometimes that we don't care, a little bit of error might not be too bad, but there's other times in life that we don't want that error. So I'm sure you've heard of the Baker dozen. So bakers, and I think they might still do it for cookies or whatever, or baked goods, they would always throw in one extra of that item. And that was because they have rules and regulations about weight. And so they always want to make sure they were within the weight limit or they could get heavily fined. So in order to make sure they were within the weight, they always threw in a little extra. I don't know if that is a great analogy. If you go and buy some product, that there's some, they want it to be not very much error, right? But they want to be as close as they can. If we're talking about, I don't know, chips in a bag, we want it, they say it's 6 ounces, they want it 6 ounces. And so they're going to try to get as close as possible to that 6 ounces.